found there's a lot of uranium in the ground. So that constraint early on, the constraint early on with EBR-1 was gone because we had this plentiful supply of uranium, and so we started deploying light water reactors thereafter. Experimental breeder reactor number 2 came online in 1964, the C4 reactor here, and then we had the fast flux reactor, and then this Clinch River breeder reactor project in the great state of Tennessee. You need to understand the genesis of where that came from. It was in 1969 where you had a congressman named Anderson from the great state of New Mexico, who was really a fast reactor proponent, a Democrat, very much in favor of nuclear technologies, rode on the airplane with President, who was the president in 1970? Nixon. This is a little bit of history here, guys, with the engineering in case you're not fully balanced. So Nixon's the president, and he convinces them that the fast breeder reactor needs to be part of the equation under the paradigm that we're constrained by uranium consumption. And so when President Nixon came out with his energy independence speech in 1971, nuclear energy was part of that, and the fast breeder reactor. And that started the Clinch River breeder reactor project. And so when that project was started in 1972 with legislation, the initial cost estimate in the congressional record was $699 million. And that got them into trouble because later on the price was more once industry like Burns & Rowe, General Electric, Westinghouse got involved. The cost estimate was on the order of about $1.2 billion. And so, and once the team started, it started moving along with it at that sort of pace. Now, there was some problems, is my interpretation of history, that it was always 7 years from completion, and there's always about $1.2 billion to complete it. And during the Carter administration, Carter was trying to stop the program because he didn't want to do any reprocessing, but Congress, Congressman Anderson and others, Congressman Gore from the state of Tennessee fought back, and Congress kept it alive, even though the president wanted it killed. And then when he switched with Reagan, Reagan had semi-support for Clinch River breeder reactor project. But in 1993, due to a lot of political issues at the time, Congress finally said, we're done, and they canceled the project virtually overnight. And that's how the, Don, did I get it correct? Pretty much? Okay. So what happened then? The Clinch River breeder reactor project, if you will, was a Titanic of the fast reactor projects. That ship was sinking, and so the liquid metal reactor program started sinking. They started the advanced liquid metal reactor program in about 1983, 84, and that started this thing called PRISM. So if you look at this, thing here, the vortex tube, it gives you kind of a history of where we're heading. So up on top is you see time from 1950 to 1994, and then at the bottom you see cost on a relative terms of how much the U.S. government was spending on the fast reactor program. You can see orders of magnitude where in the 80s was on the order of $1 billion a year. When the program stopped in 1994, the Advanced Liquid Metal Reactor program, we had one reactor design that really came out of it, and that's the PRISM reactor, called the Power Reactor Innovative Small Modular. And we'll talk a little bit more. Now with this GNEP program, the Global Nuclear Energy Partnership, you're late. We'll give you a pin, though, since you're late. To embarrass you. Okay. And so that's when General Electric in February of 2006 said, all right, we're ready to go again because we had this PRISM design. So that gives you kind of a little bit of where we're heading. Questions on the history? So let's talk about the PRISM design and a little bit of historical background. In 1981, General Electric looked at what Clinch River breeder reactor project was doing and viewed it as not an economical way to go forward. Clinch River breeder reactor was at 1,000 megawatts thermal, and it was a stepping stone to a sodium fast reactor that was going to be 3,000 megawatts thermal. General Electric said, we don't think that's scalable. We would rather go to a small modular sort of reactor on the order of 400 to 1,000 megawatts thermal and build a lot of those and get economics by replication. So in 1981, they perceived the concept, came up with the acronym of PRISM, Power Reactor Innovative Small Modular, and had some wild designs. And so in San Jose, which was our headquarters at the time, They talked about this reactor you'd lift up and float on air bearings, and then you'd refuel it and float it back. According to the history of Argonne National Laboratory, a person named Mike Lineberry showed up and explained that how you could refuel a reactor without moving it to a fuel process. And that's kind of where the genesis of the PRISM reactor design kind of got molded between really Argonne's input and GE engineers. When the Clinch River Breeder Reactor project was stopped in 1983-84, they started a program, the DOE, of two technologies. One was led by GE, which was the PRISM reactor, and the other was led by Rocketdyne, and the reactor was called SAFER. It was a competition. DOE made a decision, and PRISM became the reactor to move forward in the Advanced Liquid Metal Reactor program. General Electric had a team of a lot of different companies, Burns & Rowe, Foster Wheeler, Westinghouse, and 7 other ones that I forgot the name of, and that's how the Advanced Liquid Metal Reactor program started, and it went until 1995. Then at that point, the president was 1995, who was the President of the United States? Clinton. Canceled all nuclear energy research, so the Advanced Liquid Metal Reactor program stopped. GE then, with self-funding and funding from the Koreans and the Japanese, took the PRISM from 1995 to 2002, and they called it the Super PRISM. They went from 1,000 megawatts, from 840 megawatts thermal to 1,000 megawatts thermal. In 2002, that's when we stopped seeing retirees showing up at conferences, and it really stopped until the Global Nuclear Energy Partnership came up. Now, one of the interesting things about this reactor design is in 1987, General Electric prepared 2,400 pages of documentation and gave that to the NRC. In 1994, the NRC came back with their preliminary safety design analysis and said that this is a prudent design, and we don't see any showstoppers for deployment of the reactor. So what we have is really America's fast reactor that's been reviewed, if you will, by the Nuclear Regulatory Commission and provides a prudent starting point for us if we choose to go down this trail of the PRISM reactor. Here's kind of the genesis of how the reactor started. It was initially 3 reactors side by side. They each fed 1 steam generator. That steam was combined into 1 turbine generator to 421. That was what we called Mod A. We went to Mod B, where we put 2 reactors in the silo at 840 megawatts thermal, and then they powered a turbine. And then Super PRISM just took out a row of fuel elements and got to 1,000 megawatts thermal. And we saw that as a better viable thing rather than a large monolith sort of fast reactor where you have to have a lot of different loops. One of the reasons for that is that to scale up a light water reactor here on your right, it's easy to do because you just double the size of your components, make the pipes bigger. And so the complexity of the system doesn't increase as you scale. However, because sodium is not a very good coolant as compared to water, its heat capacity is a lot less than water, so you have to flow a lot more, but it has a great heat transfer coefficient. So you end up with a lot of stresses in your pipes. So the limiting factor is how big you can make a pipe. And so what GE came up with is about a meter in diameter. It's about how big you can make a pipe. And so from that, you have to scale either by adding additional loops onto your reactor if you want to make bigger power. So the complexity goes up when you scale up in size as compared to a light water reactor. You just make things bigger. And so that led to this modular versus a monolith sort of fast reactor, where the PRISM reactor shown here in this black and white is 1 reactor that has 2 intermediate heat exchangers that feeds 1 steam generator, and then they share a turbine. As compared to a Super Phoenix sort of reactor where you have a lot of different loops and your availability is dependent on everything working together, where this, you have the ability to essentially spin that turbine 100% of the time if you do your refueling so they're sequenced. So this part will dive a little bit more into the details of the PRISM reactor, talk a little bit about the design. GE initially started with their fast reactor program of using oxide-based fuels. And during the Advanced Liquid Metal Reactor program, they switched to metal-based fuels. But if you look back at the documentation, GE looked at oxide-based fuels, metal-based fuels, and nitride-based fuels. And this gives you a core layout for a metal-based fuel. So which is better, metal or oxide fuel? And I was warned by the people that were filming it not to ask questions because nobody will respond. Here's some data for you to take a look at. This is a cross-section of a fuel pin. And up on top here, somebody got out a file and filed it flat intentionally so that you could get a fuel element failure. This is metal fuel. And because metal fuel swells considerably when you irradiate it, what is done is you cast the metal slug in the center to be a lot smaller diameter. So the smear density is on the order of 75%. But you have this huge gap between the cladding and the metal, and so to reduce that gap conductance, you fill it with liquid sodium. And so now you get, it's called a sodium bond. And now the heat goes out, and the sodium isn't reactive with the metal fuel. So when you have a fuel element failure with the sodium on the outside, you do get fission product gases and fission products coming out into your coolant, but you don't have a degradation of the metal fuel per se. On the other hand, with an oxide-based fuel, you make the tolerances very close, and you put that oxide pellet in. It doesn't grow, even as close as much as metal fuel, but if that breaks down and gets in contact with the coolant, then you end up with these interactions, and you have problems with the oxide fuel. So that's one of the many reasons why GE favors a metal fuel over an oxide fuel. And realize this was a big transformation because GE was part of building a test reactor in Arkansas to prove that oxide fuels not only worked, but they were safe and they had a Doppler feedback. And GE had to turn from that early work from 1965 to 1971 and change really their kind of core decision in about 1988 to say they're going to do metal fuel. If you go to an A&S conference, which I hope you all have an opportunity to go to, the debate still rages on whether a metal reactor or a fast reactor should be metal or oxide. And I would submit to you, I think a metal is probably a better place to go because there's a lot of safety issues and design issues that would offer a better. And one of the things that Department of Energy did in the late 80s is did a task force and study, and their technical conclusion was to go with a metal-based fuel. This is a cross-section of the reactor vessel. These are electromagnetic pumps that have no moving parts. It takes a suction, the sodium goes up. There's a pipe that isn't shown on this cutaway. Takes the coolant at the bottom of the reactor core, flows up by the fuel, which is a HT9 cladding with the metal fuel inside, goes up, goes into the top of this intermediate heat exchanger, comes back down, and then it comes back and gets recycled. This up here is where the fuel elements, after they've been in the core, are stored. So you get some cooling and some reflection, so you don't get as much neutrons against the reactor vessel. This is in-core in-fueling or a refueling machine that's on top. This reactor vessel is about 60 feet tall. It's about 30 feet in diameter, and it's made out of 3/16 stainless steel, about 2 inches thick. One of the interesting things about that is General Electric in the United States today could fabricate that reactor vessel at our facility in Pennsylvania. We have a fabrication shop. And when we look at reactor deployments, especially in a light water reactor, very large forgings, there's really only one contender right now.